Hey guys, today's video is about motion, including both linear and angular. If at any stage it becomes too tricky to understand, make sure you pause and have a look on YouTube elsewhere for the terms that I'm describing. There's heaps of videos out there that describe it, and it is difficult to understand because it's basically physics but in sport, which is what we call biomechanics. Alright, so motion in general is split up into two things, linear and angular. Linear means it's in a line, angular means it's rotating on an angle. So linear we can divide up into two things, rectilinear and curvilinear, and I'll explain what they are in a minute. So definition of linear motion is movement of the body where all parts move in the same direction at the same time along a line. So a really great example that I've got there for you is a picture of the downhill skier. Now the downhill skier, you can see all his body parts are tucked in. They're all moving at the same speed, they're moving in the same line, and they're all moving in the same direction. And so that's a perfect example of rectilinear motion. The only difference that rectilinear has to curvilinear is curvilinear means it's going in a curve or an arc, sort of like a rainbow shape. So it doesn't mean it's actually rotating, so it's a little bit of a poor example I've got there because the snowboarder actually is rotating during their flip. But the picture of it, the snowboarder itself, really demonstrates the curve that they follow when they jump up and over the jump. And if you took the flip out of it, it would be a perfect example of curvilinear motion. So both rectilinear and curvilinear both represent linear motion. It's when you talk about linear motion, it will be one of those two. If we look at angular motion, however, it means that the movement of the body or a body part will be moving around an axis. So that means it's a central point, and that central point doesn't actually move and something rotates around it. So I've got an example there. It's a little bit tricky for you to see, but it's actually a golf swing. And so the golf club and the arms will be the body and the body parts, and they will move around a central axis, which would be the shoulder, to complete a 360-degree swing, or even more in some cases. So linear motion can be used to describe a few different concepts, two of which are distance and displacement. So distance and displacement are sometimes a little bit confusing, but if you look at the diagram, it explains it really well. So distance there you can see is in the red. Distance means that it's just the path that you traveled from A to B. So the actual area where something moved. In this case, it's from the tree to the house to the tree, so A to B to C. And in total, that was 7 meters. Now, if you were looking down on this map, as we are right now, and you drew a straight line from the start to the finish without considering any of the path in between, that would be displacement. So it's basically the change in your position from A to B, or in this case it's A to C. Now if you travelled back to the tree again, so you went A, B, C and then back to A, your displacement would actually be 0 because your change in position was 0 meters. You ended up in the same place that you started. You can't draw a straight line from the start to the finish because the start is the finish. So displacement is a little bit tricky to understand, but so long as you draw a straight line from the start to the end, that's how far the displacement is. The distance considers the path travelled in between. Alright, linear motion can also be used to explain speed and velocity. Now in everyday conversation, speed and velocity are used interchangeably as the same thing. They're both basically explaining how fast you go. Speed is the distance that you travel divided by the time, so how fast it takes you to get from point A to point B. The difference between speed and velocity is velocity takes into account the direction that you travel, and that's the displacement that I mentioned earlier divided by time. So you could actually have 0 velocity if you ended up from point A and you travelled in a circle and then ended up at that point A still, a bit like on the previous diagram. You would have 0 meters as your displacement. Now 0 divided by anything is 0, so velocity always has a direction. So I've got a great example there of the car. Always in the front of a car you'll have the speedometer, and that will show you what speed you're going. Whereas say with velocity you can have a direction. And now the reason I've got the tennis racket and the baseball bat there is because when the ball hits the bat or the racket, they actually change direction. And so their velocity will change over that period of time. So they may be going in one direction. As soon as the racket or the bat hits it, goes in the opposite direction, the velocity will change. Okay, acceleration is the rate of change of velocity over time. So you improve, or you might increase your velocity over time. That would mean that you're accelerating. If you decreased your velocity over time, that would mean you're decelerating. So we'll have a look at a couple of tables. So you've got acceleration there and no acceleration. If you look at the yellow table, when you're not accelerating, your velocity stays constant. That means that after 1 second, you're going 2 meters a second, but then after that, you're still going 2 meters a second. At 5 seconds, you're still going 2 meters a second. You haven't increased your speed at all. And on the last column there, it says change in velocity. Well, you haven't changed your velocity because it's still going the same rate. So it's 0 all the way through after 1 second. 0 meters per second is your velocity. Acceleration, on the other hand, on the left-hand column in green, that will mean that your velocity actually changes. So if we look at 1 second, the person's velocity might be 2 meters a second. At 3 seconds, it could be 3 meters a second. At 5 seconds, it could be 5 meters a second. So that rate of velocity is actually changing, it's increasing, and that means acceleration. If the change in velocity was getting smaller, that would mean deceleration. Alright, angular motion is pretty tricky, but gymnastics is the best sport to explain this. So in angular motion, you also have distance and displacement, but instead of using meters, you use degrees, which is what you get from circles when you measure them. So angular distance is the total number of angular changes during a rotation. And I've got a picture there of an athlete who is making a change on an angular axis. So he's going around that central bar and changing his angular position. Angular displacement, on the other hand, is just the difference between the initial and the final angular position during that rotation. So for example, if that gymnast started at the top of the bar and then they finished their rotation at the top of the bar again, then their angular distance would be 360 degrees because it goes all the way around that one central axis. However, if we're talking about displacement, then you're starting from the top, go to the bottom, which is 180 degrees, but then finish back up at the top again, then that actual difference is 0. So the angular distance would be 360 degrees because he's traveled that far, but the actual difference between where he started and where he finished is 0 degrees because he started in and finished in the same spot. If we measured the athlete's displacement between each of those purple dots on the diagram, his displacement and his distance would be the same. So if he did 1/2 of the bar, so say he was starting at the top and he just sort of let his body fall down and finished at the bottom, he would have traveled 180 degrees and he would have had 180 degrees difference between his start and finishing point. Alright, angular motion can also explain speed and velocity, and this is where it gets tricky. So angular speed is the angular distance travelled divided by the time taken to cover the distance. So for example, again, if that gymnast did 360 degrees of that whole bar, the speed would be how long it takes him to get to that point. Angular velocity is the rate of change of angular displacement over time. Now, a really good example of this is, and I can't get this unless it's video, is when the athlete does their 360 degrees rotation around the bar, but then they actually turn around and face the other way and change direction. So that would be a change in velocity. They also reach a point of zero movement at the top of the bar when they're changing. So that would also be represented by velocity and not speed. And just looking at that green bar there, you can measure, say the athlete again drops just 180 degrees. You can measure from point A to point B their angular velocity using that distance. Alright, so angular acceleration is the rate of change of angular velocity, and it's measured in degrees per second. Now, I'll give you a really good example of this again on the bar. This is the high bar in gymnastics. So the athlete might have a really slow acceleration at the top where the yellow star is, and that is because gravity is not really playing a part in pulling them down. But when they get to point 6, where the next yellow star is, gravity has really taken effect on them, and they're at quite a rapid velocity. Now, when they get to a later point in that swing, which is about 270 degrees, then the athlete has had gravity drawing them back down and pulling them back the other way. So they're actually slowing down. So that could be the deceleration. So we're looking at the points at which an athlete can gain the most momentum. Now, it's important to measure these speeds, especially for elite athletes, because they can see where their weak points are and train for those points. So angular acceleration is actually quite important for any athlete that has a swing motion in their athletic performance, say for example a hammer throw or a golf swing, or in this case we've got gymnastics. Alright, there's one last definition, and this doesn't really link into the others, but it explains why they happen, and that's torque. Now torque is not the actual verbal speaking torque, and it's spelt differently. Torque is the force that actually causes an object to rotate. So it's actually determined by the size of the lever arm and the force applied. And that basically means that the longer the thing that is swinging, the higher the torque. And the more force that's applied, also the higher the torque. So there's more swinging motion and there's more force that's causing something to rotate if something is longer and something is heavier, or there's more force. So if you've got a golf club, for example, and it's a very heavy golf club, obviously more force is going to be applied, and then there's going to be more torque. If you've got a long golf club, again, there's going to be more torque. So just in summary, there's two types of motion, linear and angular, and they both create general motion. There's different body parts that may follow different types of motion at the same time, especially if you're, say, cycling, or you've got a gymnastics routine where there's lots of different things going on. And then if you look at linear motion, it's all of the body parts moving together in a straight or curved line at the same time, whereas angular motion is when the body is rotating around a central axis. Don't forget that velocity is speed with a direction. Acceleration is a change in velocity, whether it's faster or slower, and torque is the force that causes something to rotate. Thanks for watching. We'll definitely go over these more in class. They're a little bit tricky to understand, but hopefully you'll be able to reach an understanding at some stage.